chapter. Let's get going on that. So first off, acids are recognized by their sour taste. Some examples of acid, like we used the other day: acetic acid, a major component of vinegar, citric acid, and lemons. Bases are really characterized by their bitter taste. They have a slippery feel. A lot of hand soaps, drain cleaners, those type of things are bases. When we talk about being basic, it is sometimes referred to as being alkaline. And as we'll talk about, a lot of strong bases come from group 1 and group 2 on the periodic table, which is our alkali metals and our alkaline earth metals. So a lot of those guys with some hydroxide is where a lot of our bases really sort of come from. Now, sort of an early definition of an acid and base is was done by Arrhenius. He did a lot of work with electrolytes. And remember, electrolytes are things that when they do go into solution, they break apart into ions. And there's really two types of electrolytes, as we talked about: strong electrolyte, which 100% breaks apart in solution. You pretty much have none of the whole unit still together. You have pretty much all ions that are floating around. The other type of electrolyte is a weak electrolyte, and a weak electrolyte will mainly stay together in solution, but will still be able to break apart a little bit. It will produce a little bit of ions. So sort of strong electrolytes, weak electrolytes are also what we sort of think about when we think about acids and bases. We have, as we'll talk about, some strong acids that completely break apart and do not stay together in solution. And we have some weak acids that will mainly stay together, but still, again, able to produce some ions. And in terms of the acid, sort of H plus being able to be produced in solution. And the same thing with bases. We have a lot of strong bases that will 100% break apart into solution. They're really strong bases, strong electrolytes. And we have a number of weak bases that will mainly stay together and still be able to kind of break apart a little bit. So an acid is defined as being able to produce the hydrogen ion in an aqueous solution. So what makes something an acid, or the ability of it to be an acid, is the ability to produce really H plus ions in solution. So the ability to produce those ions in solution is what makes an acid. And when we talk about that, what we're talking about is actually the production of free H plus. So basically the H plus ions are not attached to anything. They're floating around in sort of the water part, the aqueous part of the solution. And that's really what makes something an acid. Also really important, sort of an acid-base chemistry. When we look at H plus, it is what is referred to obviously as the hydrogen ion. We also will see H3O plus used as well. And for all intents purposes, H3O plus and H plus are essentially going to be the same. This is what is known as the hydronium ion. And they are sort of interchangeable, both in sort of formulas and equations, and also, like I said, sort of in formulas as well. I personally will use H plus most of the time, but anywhere I sort of use H plus, H3O plus, it's basically kind of the same thing. In addition, H plus is also sometimes referred to as a proton, and that's because hydrogen has one proton and one electron and no neutrons, which means in order for it to become positively charged, it had to lose an electron, which means all that's left is a proton. So sometimes it's referred to as a proton in the case of acid-base chemistry. So when something is sort of an acid, it has that ability to produce those H plus ions that are floating around in the solution. Again, not attached to anything. Same thing with our base. A base is something that has the ability to produce hydroxide ions, so OH minus ions in solution. And it's the same idea here. We are producing OH minus ions that are really sort of free flowing, if you will, by themselves in solution. And as we'll see in this chapter, sort of the ratio of those two things in terms of a solution, the H plus and OH minus concentrations, whichever one's larger will basically tell you whether or not that solution is acidic or basic. If the H plus part is larger, then it's going to be more of an acidic solution. If you have more of the OH minus floating around in the solution, it will be basic. So there is a relationship of those two. By the way, those two things, when you put them together, make water, right? H plus, OH minus, right? So in solution, we basically have both of those things floating around. But again, if it's more of an acidic solution, you have more of the H plus floating around. If it's a basic, you will have more of the OH minus floating around. So if we take some hydrogen chloride gas and sort of bubble it through water, this is where we get our hydrochloric acid. And same idea here, we dissolve some sodium hydroxide there, we get our production of hydroxide. Also a reminder, just a refresh of what we talked about when we talked about naming, right? We did talk about how to properly name acids. And remember that when you do name acids, it is based on whether or not there is oxygen involved. So it's really the oxygen that's most important in terms of the naming of acids. And remember that if there are no oxygen, the acid would be hydro something ic acid. So this is why when this becomes the acid on the other side, that is hydrochloric acid, no oxygen involved. And this is the minus part there. If it does have oxygen, as a reminder, that then it will most likely contain one of those polyatomic ions that we talked about. And if you remember, pretty much most of those polyatomic ions end in ate or ite. And if the polyatomic ion ends in ate, the acid is something ic acid, like HNO3 here. And that is nitrate, which means this will become nitric acid, right? So again, that is the proper way of naming that. If our polyatomic ion ends in ite, it will be something OUS acid. And again, here, if we just take our guy that's related to this guy, HNO2, NO2 is nitrite. So this would be nitrous acid. So just a quick reminder of the nomenclature of acids. You should know, obviously, still how to name them, because in case you get an acid or something, just the words, you'll be able to translate that into hopefully the proper formula. Also, the difference here, right? HCl and the G, or gas phase, is referred to as being hydrogen chloride. Acids typically are aqueous solutions. So acids typically will have that aqueous symbol written next to it to indicate that it is the acid and that it is in solution and it is really kind of really falling apart, and the ions are there. Any questions on that there? Now, it was a good sort of first step there in terms of acid and bases. It was limited, as he did focus for a lot of sort of hydroxide sort of field bases. As we'll learn, as we'll talk about, not all bases actually have OH minus in their actual formula, but they are able to, for example, produce OH minus in solution, which does make them bases. So sometimes people think bases always has to have OH minus in the formula, and they don't. A lot of strong bases always have OH minus in the formula, but some weak bases actually do not have OH minus in their formula. So for example, if we look at something like, as we'll see, probably NH3, which is a weak base, when it reacts with water, it will actually take an H plus from water. The result of that is you'll make NH4 plus and OH minus. So in this case, we are still able to produce some OH minus in solution. And that makes NH3 a base, but it needs to obviously do a little bit of work there to produce the hydroxide. So it is a weaker base than something like sodium hydroxide, which will completely break apart in solution and just need to go for a swim, basically. and it will produce a hydroxide there in a lot of amounts. Yes, sir. Yeah, so we're going to focus mainly on these guys as our strong ones, the guys that do have hydroxide in this class. Now, in addition, as we talked about, electrolytes, NH3 is a weak base, which means it's a weak electrolyte. So again, if you remember, weak electrolytes typically have those arrows heading in both directions. So again, you'll probably see those things for weak acids and weak bases. Our arrows kind of heading in both directions, as opposed to something like sodium hydroxide that's considered a strong, which has a one-way street sort of arrow. Everybody's basically going to the product side. So the more sort of common definition of acid and bases that most people sort of look at is one that's known as the Bronsted Lowry definition of an acid and a base. And in a Bronsted Lowry definition of an acid and base, an acid is a proton donor, so that is something that will give away an H+, and base is a proton acceptor, so that's something that will accept the H+. So it's really important that when somebody gives away an H+ and somebody gains an H+, that you think about it as not just an H that's being transferred, but also the positive part of it that does have an effect on the overall sign. So for example, we could actually use the one I just did as an example. In this particular case, it is the water that's going to really donate the H+ over to the NH3. In this case, that's going to make the water the acid. The NH3 will accept the H+, which will make the NH3 the base. The result of that is, and the result of sort of the Bronsted Lowry definition is, when that transfer of the H+ happens, we actually create some partners on the other side that are related to the original acid and bases. And the partners are these guys here. The base on this side, its partner on the other side is what is known as the conjugate acid. And the acid on the other side, its partner is what is referred to as the conjugate base. So what is the relationship between the guy on the left-hand side of the arrow and the guy on the right-hand side of the arrow? The relationship is this right here. It is the H+ that's being transferred. So the only difference between those two things, between the base and its conjugate acid and the acid and its conjugate base, is actually just one H+ difference. So the only difference is one H+ difference. In order for those things to be pairs, as we see, what happens with the base is it accepts the H and it also accepts the plus part of it, which means the NH3 was neutral to begin with. Over here, if you just look at the difference between those two, we added an H and we also added the positive charge to it. So that's how we get NH4+. And when we look at the water, it loses not just the H, but it also loses the plus. So when it loses the H, you're left with an O and an H. And when you lose a positive charge, you become one more negative. So water was neutral, so it goes from no charge to a -1 charge. So that's really the important part, and sometimes people struggle with, is the positive part of the H+. And again, if you gain an H+, you should become one more positive in terms of the charge. And if you lose an H+, you should become one more negative than you started with. So again, the charge part of it's really important to remember. Yes. Yeah, so technically speaking, the Bronsted Lowry definition, the water here is acting as the acid, is the one that's going to donate the H+ over to the NH3, which will accept it. So the NH3 will be acting as a base. It is kind of a weird idea for some people to think of water as an acid. As we will see, water can also act as a base as well and accept the H plus. So something that could act as an acid or base, as we'll talk about, are things that are amphoteric. Yes, sir. There you go. There you go. Yep. Exactly. So in this case, the reversible reaction is the opposite that's sort of happening. And it doesn't necessarily always has to be sort of a reversible reaction where you see conjugate acid, conjugate base pairs. You could also deal with strong acids and strong bases. So they do have pairs on the other side. But the relationship is this in terms of the equation. The kind of regular acid and base is always on the left-hand side of the arrow, and the conjugate partners are usually found on the right-hand side of the arrow. Yeah. So there are certain things as we go through this chapter that you will kind of know, like this thing is sort of an acid or this thing's sort of a base. So that's the main sort of probably route for us in this class that you would use to know that, hey, you know, this is going to what's going to happen. In reality, it is a reaction that's taking place, but this is really just what's happened when you put something like ammonia in water. And sometimes we may not even include the water. It's not it is a reaction, but it's not a reaction like we're taking kind of two different substances, if you will, like an acid and base together type of reaction. But this is still a reaction that's happening between that substance and water when it's sort of in solution. And we can have sort of the same idea if we look at, say, even hydrochloric acid, for example. If we take hydrochloric acid, one way we can represent hydrochloric acid as sort of dissociating or breaking apart in water is to actually include the water in the equation. And in this particular case, what's going to actually happen is because HCl is an acid, it's actually going to donate the H plus to the water. So in this case, the water is actually doing the opposite effect here. It's going to actually accept the H plus in this case, which in this reaction actually makes the water the base. And in this case, the acid, as we would expect, is the HCl, which is hydrochloric acid. When it does so, it's going to create H3O plus and Cl minus. And in this case, the two things that are related to each other are these guys here, the HCl and the Cl minus, and that would be the conjugate base on the right-hand side here, while the water here is actually acting as the base, which means the H3O plus, which is our hydronium ion, is going to be our conjugate acid. So you could have that again in sort of both situations, either stronger or weak acid or base. You could have these type of reactions. Now, we talked about earlier that H plus and H3O plus are sort of interchangeable. And really what we're looking at here, for example, in this reaction I just wrote is the dissociation of a strong acid. Basically, the strong acid is breaking apart in solution. You could also sort of write this reaction, and it is acceptable, you know, just to write HCl because it's a strong acid will just 100% break apart into H plus and Cl minus. Now, in this case, I didn't really put the water in to show the base part of it, but they are equivalent sort of reactions. Basically, we're just dumping basically hydrochloric acid in a solution of water. So when we do include water in the reaction, which is oftentimes done in books and stuff like that, that's really how you'll kind of generate the H3O plus part, which is the acid part. When you kind of ignore the water aspect, which is also very commonly done when you're just writing like an acid breaking apart or even a base sort of breaking apart, more so with the acids, you'll just get the H plus. So that's why those two things are sort of equivalents to each other, and you can sort of interchange those things. Now, really the difference here between the acid and its conjugate base or the base and its conjugate acid is only that one H plus. So as we go from the acid to the conjugate base, it has one less H plus. And as we go from the base to the conjugate acid, it has one more H plus. Importance of that is, in order for those guys to be pairs, that can be the only difference between those two substances is one single H plus. So if you're trying to compare two things and see if they are related to each other as either an acid conjugate base or a base and conjugate acid, the 100% only difference that can be between them is one H plus. Anything more than one H plus, another element, something else, two H pluses, three H pluses, they are not related to each other in terms of the Bronsted Lowry definition. Any questions on that? So as we sort of jumped a little bit ahead, in general, the general reaction here, HA is what's referred to as just an acid. HA is what is referred to as a monoprotic acid, and it's sort of a generic formula if you're not sure what acid you're dealing with, but you just know it's sort of monoprotic acid, you could use HA. So an actual real life example would be something like hydrochloric acid is like a monoprotic acid. Monoprotic means it has one H plus it's able to give. You could also have a generic formula for H2A. This is what is sometimes referred to as a diprotic acid. And a diprotic acid has two H pluses that can sort of come off. The H pluses, as we'll talk about probably a little bit later on this chapter, actually do come off basically one at a time. They do not basically just both drop off. It is actually a stepwise sort of fashion as to how those H pluses come off. An example of this in sort of real life would be something like, not that, it had sulfuric acid, like a P, but really an S would be better there. Let's try that. So H2SO4 is an example of a diprotic acid. Again, it has the ability to kind of away two protons. And there's also triprotic acid, which is sometimes generically just abbreviated like H3A. And that is sometimes referred to as a triprotic acid. And that an example of that in real life would be H3PO4, phosphoric acid. It has three hydrogens that basically could come off. So the importance of this is actually, if you ever need to sort of use the more generic and you're not using maybe a real form of something, is the A part. So for an acid, all acids, the cation or the positive guy is the H plus. So the H plus is always the positive part of it. And that means that when we look at something like this, the A actually has a -1 charge, like the Cl here has a -1 charge. When we look at this, because there's two hydrogens, the A here actually has a -2 charge, like what we see with sulfate, it has a -2 charge. And here, because there's three hydrogens, the A actually has a -3 charge, like we see in a real life example of phosphate that has a -3 charge. So it's important to remember that, you know, when these things sort of break apart or when they have those guys there and you want to write the right formulas, again, it's always H plus for the cation, but the negative guy may have multiple different charges you want to keep track of. Yeah. For what now? There would be if we kind of get a little bit ahead of it here, but what happen is it would lose one H plus, so it would drop off, and you would be left with HSO4 minus. The guy minus one H plus that came off. Now, what would happen is this guy that's already sort of lost an H plus will then come and lose a second H plus, and you will create basically sulfate. So to answer your question, this would be really the acid here. And this guy here would be its conjugate base. This guy and this sort of Bronsted Lowry definition. The only difference that there can be between those two guys is one H plus, because they really do come off basically one. To say that those guys are an acid conjugate base pair, but the difference there is two H pluses, so they would not be a pair. The only pairings that we have is basically this guy and this guy, which the only difference there is one H plus, and this guy and this guy, where the only difference is also one H plus. But again, when we kind of jump from like this guy to this guy, we are now obviously doing multiple steps. So there's definitely a difference of more than one H plus. So those two guys, kind of on the red diagonal there, would not be pairs because of that. Any questions on that there? Now, sometimes in a class like this or a lower level sort of chemistry class, you know, we think of these acids as would be losing both hydrogens at once, because oftentimes when we look at the reaction, for example, like what we did when we did titration problems, we look at sort of the overall reaction of what's sort of taking place, and you can get the overall reaction by adding these two guys together. And when you add these two individual steps together, anything that's on opposite sides of the arrow can cancel. Anything on the left-hand side will stay on the left, and anything on the right will stay. Really what cancels when we think about the overall reaction is this. And that's why we oftentimes will say, you know, it's a diprotic acid. And sometimes people think, well, there's two hydrogens there. It sort of does imply that, you know, this guy will kind of drop both hydrogens at once. But again, it is sort of a stepwise fashion at which it does. And it does happen in each case here. Any questions on that there? Okay. So overall, the process does happen. It is, as we'll talk a little bit about, much harder to remove the second hydrogen than the first. So the first comes off relatively easy. The second one is a much harder one. And in the case of a triprotic acid, it is much harder to get rid of the third one than, say, the second one or the first one. Yeah. Question? No? Good. Yeah. That is true. And that's, you'll learn a lot about that in Chem 1B when you go there. All right. So talking about conjugated acid base pairs. Again, the only difference, as we've gone through a number of these examples so far here, can only really be that one H plus difference. And that's what you want to look at when you're trying to evaluate, you know, are these things pairs or not pairs? And as I mentioned before, we always find just a regular sort of acid and bases on the left-hand side of the arrow, the sort of conjugate partners on the right-hand side of the arrow. So here's again just a process of making it. And in the case of hydrogen chloride here, we will leave off an H plus and get our guys that are related to each other. And again, that's the formation of the hydronium ion, which looks like that there in the brackets. All right, so take a second here and evaluate each of these and determine, are any of these a conjugate acid? Look, and really, hopefully at this point, you should know that really what you're looking at is H plus. So again, that is really the only difference between those two to allow them to be pairs. So really, you can evaluate one of two ways if you want. You could rewrite them both if you like. And you could take an H and a plus off of the first guy. So we take off an H and we take off a plus, so it becomes one more minus, and now we have a guy that's matched what was on the other side. So the first one here looks like it should be a pair, as the only difference is that one H plus. For the second one here, we have HCl and ClO minus. Again, if we take off the H from the acid and the plus, we should end up with Cl minus. And that is not what we end up with here. The guy has an oxygen, so that would not be a pair. Any question on those two? We take a look at H2PO4 minus and HPO4 2 minus. If we take off an H and we take off a plus, we then become one more minus. HPO4 2 minus matches on both sides, so those guys would be pairs. And lastly here, HNO3 NO3 minus. Once again, taking off the H and the plus coming off will make that more minus, and they match. So that would be a pair. By the way, I knew perhaps in this pair that the one that was the acid is typically the one that has the extra hydrogen, is sort of how you could kind of remember that. Will typically be the guy that has the extra hydrogen. So in this case, it looks like it is 1, 3, and 4 are winners in this case. Any question on those there? All right, so for these guys here, why don't you write the conjugate base? So write the formula for the conjugate. Okay, so let's take a look. So once again, really you should know that the difference would be that H plus, but oftentimes people have the question of, should I put it on or should I take off the H plus? So the way you can really sort of think about it is about the definitions of an acid and base and the relationships that we talked about. We always know that on a reaction, there's an acid, there's a base, and on the other side, there is a conjugate acid and a conjugate base. And the acid on one side is related to the conjugate base on the other, and the base on one side is related to the conjugate acid on the other. So in this particular example, they told us that we want to write the conjugate base. So we basically want to end up over here, which means if we think about this backwards, everything that we are starting with on this problem is an acid. And at that point, all you have to think about is the Bronsted Lowry definition of an acid, which is it should donate the H plus. So you can kind of think of it backwards to figure out what you're dealing with. Once you figure out what you're dealing with, you can just basically follow the definition. They will not, like in this problem, always tell you, hey, these are all acids or these are bases and stuff like that. So they'll kind of do that. With that being said, we now know that pretty much all we have to do is take off the H and the plus. So when we take off the H from the first guy, we end up with HS. Once again, the plus means that we're going to then become one more negative. So this would be HS minus, should be that guy. Same thing here. This is going to lose an H. When we lose an H, we end up with just an S that's left over. Once again, we lose the plus, which means we're going to become one more negative. So we are already -1 here. So we will then become one more negative, which would be S2 minus. Any question on those two there? Coming here, we're going to lose an H. That leaves us 1 nitrogen and 2 hydrogens. Once again, here we are neutral, which means when we lose the plus, we will become one more negative. So we'll end up with NH2 minus. And lastly here, we will lose 1 H, which will leave us an H, an S, an O, and a 3. And once again, it is neutral, so it becomes one more negative, and we end up with HSO3 minus. Any questions on any of those? Yeah. Exactly. So if you were looking for the conjugate acid in these cases, that would mean that what you were starting with was a base. And as you said, basically that means we're just going to add an H plus to each of them. Yeah. So why don't we look at one? Let's say we had HCO3 minus, a little bicarbonate here. Why don't you write the formula for the conjugate acid? And why don't you also do it for the conjugate base? Starting with, we'll start with the conjugate acid in this case. So as we just talked about with the question there, if we are looking for the conjugate acid following backwards, that means that what we're dealing with in this case is going to act as a base, which means it should accept the H plus. So in this case, we actually want to put the H plus on. So when we put an H on, we end up with 2 hydrogens, still the CO3. And then the +1 and -1 equals 0 when you have those together, right? So plus and minus. So we get to a neutral guy going in that direction. Now, when we go the other way, like we did in this example, we're looking for the conjugate base, which means, once again, if we back it up, in this case, it's going to act as an acid, which means it's going to donate its H plus. And when it does so, we will lose the H, which leaves us just a CO3, We started at -1, we become one more negative, we end up with carbonate. So once again, this guy in the middle, these two are partners, these two are partners, but once again, going from the outside to there are not partners because that's obviously a 2 run of H pluses. Question, yeah. How did I get the charge? Yeah, so whenever you lose an H plus, in addition to the hydrogen, what happens because it's actually a plus is you become one more negative in terms of the charge. So it already started at a -1. So when it loses one more positive, it kind of has one extra negative that's now going to be outweighing the positives there. Basically has more electrons than protons. So it has one more electron than the protons, and it'll become -2 in that case. Other questions? So this again is something that's amphoteric. It could act as an acid or base in certain situations. Typically speaking, if you run across anybody that comes from kind of like a diprotic acid or a triprotic acid, they have that extra hydrogen and a charge. Those are the guys that do have the ability typically to do that, either go one way or the other, because they have the hydrogen to give, and they also can accept the hydrogen because they have that negative charge. Clearly something, if you had just F minus, it can only act as a base, right? Because it cannot act as an acid because it doesn't have a hydrogen to give. So F minus, for example, is another kind of weak base that it could actually work as a base, but definitely would have no chance of being an acid because it has no hydrogen to give. Any questions on that there? So let's talk a little bit about acid strength. As we talked about, in certain cases, an acid can really act as a weak electrolyte and kind of head in both directions. And we get those arrows that do go both ways. So originally, kind of the forward direction will make our H3O plus and A minus, but at some point, those guys will have enough of a concentration that they actually can, in a weak acid situation, kind of head back the other way. And we get this sort of back and forth for a weak acid. And that really is, you know, like I said, a weak electrolyte, which again is why we do see those arrows heading in both directions for that. Now, if the forward direction predominates, we will have a strong acid, which means it is a strong electrolyte and will 100% break apart into ions. So it is a strong electrolyte. And that's what it means when it talks about it being completely ionized or completely dissociated. In solution, 100% of what you have in that solution are those ions. And that is different than when we have a weak acid, where it's kind of going back and forth, but mainly staying here. Again, a weak acid would be a weak electrolyte and will mainly stay together. So mainly in solution, that is what you have there, but it is able to produce a little bit of these guys here. And because it's still able to produce some H plus or H3O plus, it is still considered an acid because it has that ability to do that. But it's considered a much weaker acid, obviously, than something that is a strong acid, which all they need to do is go for a swim, and they're going to produce a lot of H plus very, very quickly in that solution. So a couple of relationships that are important is a strong acid will contain a relatively weak conjugate base. So they're sort of opposites, not extremely important for us in this class, but you should understand that relationship. When you get to 1B, it is really important to understand the relationship between a strong acid and its conjugate base, or even a strong base and its conjugate acid, or a weak acid and a weak base. So basically, if you have a strong acid, the conjugate base, and if you have a strong base, it works for bases as well, is conjugate base. This conjugate acid will be weak. If you have a weak acid, is partner conjugate base, which is conjugate base will be relatively strong. And if you have a weak base, is conjugate acid will be relatively strong. So there's sort of an opposite relationship. And there is, again, outside the scope of this class, in terms of being relatively strong, the conjugate base or conjugate acid, what that means in a normal situation is it will continue to react with water. So it has the ability to kind of continue to react with water. It could affect the pH of the solution in those situations. Even though the strong conjugate base or strong conjugate acid, they are much weaker than a strong base or strong acid by itself, but they do have the ability to continue to react. How do we know what are some strong acids? Here are some listed, just to make a list of some of the strong acids that you commonly come across in class. That's going to be your hydrochloric acid, your hydrobromic acid, your hydroiodic acid, your nitric acid, your perchloric acid, your sulfuric acid. So these are considered strong acids. You probably are pretty safe if it's not one of those 6 to assume that it's probably going to be more of a weak acid. Just some common weak acids that sometimes come across. There obviously is more than just this, but HF is a common weak acid. HNO2, nitrous acid, HCN. So these are some weak acids. But like I said, it's probably much better, and it's a good thing to know as you continue on in chemistry, and also for this class, that kind of list of strong acids is really a good thing to know as you sort of continue on. In terms of bases, a lot of strong bases do have hydroxide in them. Common ones, sodium hydroxide, potassium hydroxide. Kind of, if you look at group 1 and 2 on the periodic table, where you got your sodium and your potassium kind of coming this way and hanging over kind of that way. Any of those guys with some hydroxide, a lot of times will be a strong base in a lot of situations. As we talked about earlier, sulfuric acid obviously is a diprotic acid. So as we talked about, they do come off one at a time. And something like, say, phosphoric acid, it can lose 3 of them. It is, as we talked about, much harder to remove the second H+. If you just think about it, you end up with something that does have a negative charge, trying to remove something that's positive. So it gets much, much higher. And in the case of diprotic acids and triprotic acids, as you'll learn if you go to 1B, pretty much the majority of all the H+ that comes off from that first hydrogen. It's really the majority of all of it that comes off. Very small amounts of the second hydrogen, third hydrogen really sort of work their way off in those cases. Any questions on that there? Now, there are some acids which are referred to as oxyacids. They are basically acids that have oxygen, which is why they're called oxyacids. So, for example, our nitric acid there, like something like this. And it really is this bond here, which is a polar bond, as to where that hydrogen will basically come off of. Some organic acids have a carboxyl group, and that group is this guy here. They should have put on my weak acids. That is a popular weak acid. We used it the other day. Example for most books when you're dealing with weak acids. Yes, sir. Yep. Very good. Now, this acetic acid, again, is going to be that hydrogen that comes off of there. And that is, again, the major component of vinegar, which is what we kind of played with the other day when we did that titration. So as we saw and as we've been talking about, substances that can really act as either an acid or a base, or what are known as amphoteric substances. And here's a couple of examples that we did run through here. In this first case, we have water acting as the acid. So again, it's donating the H plus over there. And the result of that is we generate really a basic solution because we have OH minus on the base, the product side. And in this case, water is acting as the base, as it will accept the H plus in the second example, producing H3O plus. Sometimes people also have trouble trying to figure out, if you look at an equation, can you make a relatively good assumption of whether or not the solution might be acidic or basic? And you can. So typically speaking, the arrow, and you either have H plus or H3O plus sort of made there on the product side of the arrow, probably a good chance that you're some type of acid or acidic situation. If you look at the arrow and you got hydroxide there on the product side, that's usually a basic or a basic type of environment. So by looking at equations, you can sometimes make a relatively good assumption as to whether you're dealing sort of in an acid or a base type situation based on what you see produced. Now, water can even act upon itself, one being an acid, one being a base. So for example, this guy donating over an H plus, and that's what's happening in solution all the time. You got sort of the waters sort of reacting with each other. And it creates an important relationship, which is known as the autoionization of water. It creates what is referred to as Kw. And Kw is this right here, the concentration of H3O plus times OH minus equals 1 times 10 to the minus 14. I personally will use this. Kw is H plus times OH minus. And once again here, the H3O plus and the H plus, they're interchangeable. This is a constant value. And really the value that you use most of the time. In reality, it does change temperature, but pretty much if you need to use Kw, it is 1 times 10 to the minus 14. When you see the brackets, those mean concentration, and what we're talking about here is molarity, which is moles per liter. So that is what the little brackets mean, and it's the concentration of the H plus times the OH minus. Really, the H plus part is the acid part of the solution. The OH minus is the base part of the solution. And the relationship between those is as the H plus concentration increases, the OH minus concentration decreases, and vice versa. So if the H plus concentration goes down, the OH minus concentration will go up. So they run opposites of each other. And that's how you can determine whether or not a solution is acidic, basic, or neutral, by calculating either the H plus or the OH minus concentration and comparing the two numbers. If the H plus concentration is larger than the OH minus concentration, then really your solution is going to be acidic. If the OH minus concentration is larger than the H plus concentration, then your solution will be basic. And if each other, they both will have a concentration of the same. Same calculation, regardless, give you a W value there at minus 14 and divide it by whichever one they give you. Punch these numbers in. Guys, in this chapter, you're going to be off. So you definitely want to make sure those numbers into your calculator that you are using that exponent button. Otherwise, you can get into some trouble a little bit later on as well. So let's try some here. Determine the H plus or OH minus concentration for each of these, and determine is the solution in each of these cases acidic, basic, or neutral.